We're going to move to our next, the second talk, second plenary talk. This is from Veronica Lee from New College of Florida. The title is Spatial Modeling of Bird Population Using Citizen Science Data. So Veronica, please go ahead.
All right, let me go ahead and get right into it. Okay, well, hello, my name is Veronica Lee, and I am a recent graduate from New College of Florida. And I'm here today to present my research on the spatial modeling of bird populations using citizen science data. I first developed this research as my undergraduate thesis for my degree in statistics from New College, and the advisor for this research is Dr. Andrei Skripnikov. So I'll begin with a bit of background. The Cornell Lab of Ornithology is a research lab dedicated to understanding birds, and they created the Citizen Science Project eBird, where anyone can report observations of wild birds. So eBird works using something called a checklist system. So I have screenshots here to show how it works. You open up the eBird app, you start a checklist, and as you're going around looking at birds, you record what you see. Maybe you report you saw 5 mourning doves, you saw 1 turkey vulture. And then eBird records additional metadata specifically for that checklist, such as a geographic point location to represent each checklist. Additionally, all eBird checklists go through an automatic verification process. Here's an example of a checklist that has been flagged for having unusual observations. So what was my research interest? I wanted to use this data from eBird to model bird populations. I decided to focus on the region of peninsular Florida, as it is the area that I have the most experience with. I wanted to see how I could build on previous research done by the Cornell Lab, and in particular, I was interested in modeling relative abundance. Relative abundance, in the context of eBird, is the count number of individuals of a species recorded during a specific checklist. This is our stand-in for true abundance, which would be the true number of individuals of a species in a certain area at a certain time. But unfortunately, since birds are known for not staying still, we can't measure true abundance. So we use this relative abundance as our best stand-in. I was also interested in addressing potential spatial dependence. Since this is spatial observation data of the species, it may potentially have this spatial correlation. So I'll now briefly go over my covariates of interest. There were 2 types of covariates that I included in my model. The first are environmental covariates. These are related to the intrinsic properties of the circular area that is around where the checklist was recorded. So for example, over here, I have a map showing the wetland data that I used to generate the wetland covariate. And then also the checklist metadata that comes from eBird. I will now go over the previous work done by Cornell Lab researchers, Johnston et al. They had several important contributions. They created a filtering structure, in particular, filtering for complete checklists only. So we only have eBird checklists where people recorded every bird that they identified. They added the checklist covariates that I mentioned in the previous slide into the model, which is very important as it accounts for bias in the different ways that people may choose to conduct a checklist. They used negative binomial and zero-inflated Poisson distributions for relative abundance. These are generally a good fit since they are good for over-dispersed count data, which is what we generally have in our eBird data. And they use generalized additive model or GAM techniques to represent nonlinear relationships between the predictors and the response. However, a couple limitations. They did not assess if GAMs are preferred to the simpler generalized linear model or GLM. And they also used modeling techniques that assume independence of observations. This independence may be violated, however, if we see that the observations are spatially dependent. There is something that we can do in order to address this spatial dependence, which is a hierarchical generalized linear model, or HGLM, with spatially correlated random effects. The researchers Lee et al. Used a quasi-Poisson HGLM for counts from other species observation data with excess zeros, very similar to eBird data. So I'll be doing my analysis, merging techniques both from Johnston et al. And from Lee et al. To see how I can best model relative abundance data. Real quick, the data preparation. I selected 10 related species and I worked with each of their data sets separately. I applied the data filters as developed by Johnston et al., removed any non-informative covariates from my initial set, did multi-collinearity analysis, influential data analysis, and finally exploratory data analysis revealed that for all of our relative abundance data, we had an extremely severe right skew and a very large excess number of zero counts. From there, we decided to fit a quasi-Poisson, negative binomial, and zero inflated Poisson for each of these distributions, one GLM and one GAM. And we used June 2016 data to fit these models, and then June 2017 data to evaluate their predictive performance using mean absolute deviation as our metric of comparison. And from this, we found the quasi-Poisson distribution to be the best of the three. And we did in fact see that the GAM technique had enough predictive improvement over the GLM technique to be worth its additional complexity. Next, we fit a quasi-Poisson HGAM, which is a hierarchical generalized additive model with its spatial random effects. This time, we used conditional autoregressive row hat values that were able to evaluate the practical level of spatial correlation in the data. Now, as you see here, we only have 8 species instead of the 10 that we originally selected. So what happened was that the HGAMs weren't able to fit for 2 out of the 10 species. And this is because of the extreme complexity in fitting the quasi-Poisson HGAM. So this is just something worth considering. But what we also see here is that we have spatial correlation of around 0.2 that we see for the species where it did fit. So this is some notable level of correlation. Then we used our 2017 test data again to evaluate predictive performance. So we see now that going from the quasi-Poisson GAM to the quasi-Poisson HGAM, we have a very notable improvement across all 8 of the species where the HGAM was obtained. Around maybe a 20% up to even a 50% improvement in mean absolute deviation. Next, we also have effect displays, where we evaluated the effect of selected covariates on the white ibis relative abundance. And these are nonlinear because of the generalized additive model technique. So what we see here is that for the GAM fit, we see for these 2 environmental covariates over here, very extreme relationships that I don't find to be particularly realistic in the context of the white ibis. And then we do have these HGAM effect displays here that I find to be much more realistic, much more suitable to the actual relationship. Next, we have the prediction plots that I made. So these are for the study area. I held the checklist covariates constant and then predicted across the study area using the environmental covariates. And this is for the white ibis species. On the left is the quasi-Poisson GAM prediction plot, which we see has lots of areas of very low predictions, areas of very high predictions, as opposed to the HGAM prediction plot, which appears to be smoother overall, which I do find to be more realistic, given the fact that the white ibis population is in fact dispersed across this entire region. Very importantly and of note is if we zoom in on this area here, this area in South Florida, we have the wetland plot map on the left, so we can see that these dark areas of near 100% wetland habitat correspond to areas that the quasi-Poisson HGAM model predicted to have high values of relative abundance. So to conclude, we decided to prefer the quasi-Poisson HGAM with spatial effects. We found it to both have better prediction quality and also to be more realistic regarding the true impact of environmental covariates on relative abundance. This has very important implications, for example, in conservation initiatives. There were a couple limitations in this research that could be addressed with future research. We had to remove X count observations that corresponded to checklists with presence only values. And we also did not have a method available for measuring the statistical significance of spatial dependence. Instead, we only had the car row hat values able to measure the practical level of spatial dependence. Thank you very much for listening, and I hope that you enjoyed this presentation.
Thank you, Veronica. Yeah, we have a quick question from the Q&A for you. In what way did your work build on and differ from the previous studies made on this topic?
Of course. So thank you very much for this question. So the previous studies made for using eBird data did not account for or consider the potential in the spatial dependence. So the spatial dependence has to do with the true distribution of a bird population throughout a given area, because it's not like you go out to record a checklist and birds just independently come into existence. They have a specific distribution throughout the geographic area. But previous studies didn't account for this and used models that assumed that all the checklists were independent. So I created it's called a neighbor weight object. So basically considering which point locations in my checklist were close or far to each other. And I incorporated that structure into the modeling. And this is something that was already done in the research of Lee et al., which I reference in the work that you can access on the website. But they had not applied it to eBird data. So this is the first time it was being used for this eBird citizen science data. I hope that answered your question.
Yeah, I'm sure it did. So hopefully, someone who asked the question is happy with it. So thanks again, Veronica.